All right. Hello. My name is Orion Harbaugh, and today we're going to be going over the presentation for project number 2. This is called Better Than Paperclips. So our professor basically created an assignment for us to kind of work on the concepts of 3D graphing and how we could explain it to people and a few other things. So we're just going to go right ahead and start. So I've got a couple questions here from the confused students. So number one, they cannot picture how 3D stuff can work. They understand the X and Y axis, but they don't understand when you put another axis in. So can we teach them some ways to visualize stuff in 3D? So let's do that really quick. So I picked 3 basic ways to do it, from easiest to most difficult and most time consuming. So number 1 is software. So software is the easiest thing, I think, because everybody has a smartphone or an iPhone or a tablet in their pocket. So they can go search up the website or whatever, and they can type in all the formulas that they want in the specific order, and they'll get the exact graph of what it's supposed to be in 3D. Now, I agree with the professor I agree with Professor Peter in that this is actually a pretty recent development, because I don't remember having this when I was doing math for the last, it's been a couple years since I've been back into math. It's been like 3 years. And before that, I'm sure, it was Calc 2 and stuff, but our teachers never even showed us stuff like this. They had us visualize it online. They would just pull up pictures and be like, okay, this is roughly what it's supposed to look like. So I think it's really cool that we have software like this, because, if you pull up the software, you can visualize anything. You can just type it in, extend it out, and you get to see it from every single set of planes. So X, Y, and X can be seen here, and Y and Z can be seen, and X and Z can be seen. You can literally see all of the planes and see exactly how the object is formed when it's graphed in 3D. So I think that software is definitely the easiest method, because it doesn't require a lot of wear and time to do it. Now, of course, seeing stuff on a screen may not help somebody. Even if you can rotate the object around on the screen, they may have issues learning it visually, and they're kind of like, okay, I don't really understand it. In that case, if they kind of don't really understand how things are forming, they can start graphing by hand. And if they graph it by hand, there's a few things you can do. You can kind of graph each set of the three coordinates, like if we're doing it in Cartesian, or XYZ, it's pretty easy to do it that way. I think that's definitely the way to start them, is, viewing it that way, because you can see the planes just like we did in the software before. So when we graph it by hand, it's a little different. They have to kind of think about it where all the axes are intersecting together from a certain point of view. So this isometric paper here, is a great example for that. You can actually buy this stuff online. You could print it. You can definitely, use it, and you can make very basic shapes. I wouldn't try to make 3D objects in this, because that's definitely going to confuse the crap out of them. But if you do really simple stuff like circle formulas and extend them out into the z-axis, or literally anything that's like really basic to graph into the X and Y plane and push it out into the z-axis, you kind of give them a general understanding of what the concept of graphing something in 3D is supposed to be. So, there's the y-axis, there's the x-axis, there's the z-axis, and this whole thing took me like 30 seconds to do. Everything is perfectly straight. I don't have to spend a bunch of time drawing out the exact set of parameters for it, what the axis is supposed to look like. It's all pre-done and straight for me. So I definitely would support this method, especially like in a test environment. If you had to do a test on paper, this would definitely be a good way to do it. I'm sure people have done it. I don't really know. I'm not really familiar with this, because I'm taking Calculus 3 in digital mode right now online, but this would definitely be a good way to teach somebody visually, and semi by hand, because it is still hands-on. They have to draw it out, so they still have to kind of see it and graph it from each set of axes. So they can literally base each line. They can graph the points exactly the way that you want them to, so they can go, I'm graphing from the z-plane. It wants me to do, I plug in the numbers and it gives me a 1. They go all the way up here and they mark it, or whatever the number they have to mark. So pretty good. I think graphing by hand is great. The problem is it takes a really long time. It takes way longer than software. Software, you just plug in one formula. Graphing by hand, especially in 3D, will take a while. But they'll definitely understand it after they do it a couple times. Now the next thing, I call this the DIY 3D method. So basically, you're building something. So this is kind of an idea that I had. I came up with this for fun. I was kind of like, okay, this is kind of neat. Because I liked our teacher's paperclip idea, visualizing stuff with physical objects like paperclips. Now, you can also use your right hand. That's another thing you can do, is kind of teach somebody the right hand rule, and they can kind of see the axes with their thumb and forefinger and stuff. And when they're doing things with paper or with the formulas and the software, that helps too. But a really good way to do it with objects in reality, in real life, is to create something that'll simulate it. So I had an idea for making one where it's like a cage. You make this big cage, that has all the axes on it, and it has, all the sides of the cage are open. The only ones that are closed are the ones where it's the X and Y axis on the top, bottom, and the top, so you can just kind of lay it down somewhere and put everything on. And what you have to do is you take the graph, maybe you have the graph on paper, maybe you have all the points out already laid out in a little matrix or something that you've created. You've already done everything. What you have to do now is you have to take you create this little cage with whatever you want, Legos, Connects, whatever, and you have the chicken wire on top that's supposed to represent each piece of the axis. You can mark the sides of it too, and you can mark the middle parts for what the axes are. You take your strings, and you start tying them to the edges, or you put little clips on them. You could probably hook them with paper clips, actually. So this is kind of a really cool idea. I thought it would kind of expand on the teacher's ideas. These could be like little paper clips. And they would have strings tied to them, and you would just put little balls on the end that would represent what the little intersection points are of where that point is supposed to stop, where it's supposed to intersect with all 3 points and make up that little piece of the object. And you just lay them out. It'll take you hours to do, I'm sure. But you put it all together, and you'll kind of have a rough visual of what the object is supposed to look like. It's not going to be perfect. It's not going to make a 3D thing. It's just going to be like you literally have like one atom every 10 atoms of something that you made. So you're just going to see like the rough skeleton of it. You're not even just little pieces of it. You're not going to see the whole thing, but it's definitely a better way to visualize it, I think, than anything else, because you're going to build it in person. You'll spend all the time on it, and you'll really understand what the concepts are when it comes to graphing something in 3D. So yeah, I think these 3 methods are definitely the best ways to do it, but they all do have their drawbacks. You'll probably learn the most from 3D because you'll have the tactile, visual, everything. Everything will be right there. Tactile, visual, and mathematical-based learning. You'll be doing all that to figure it out. You'll definitely learn it. If you do it a couple times, I'm sure you'll have some pretty good understandings of it. Then graphing by hand, you'll still have to do a lot of the math, and you'll have to draw on a piece of paper, so it's a lot of tactile stuff still. But you'll definitely have to kind of comprehend the fact that you're on a piece of paper that's kind of providing the illusion that you have 3D. But it's pretty close, so it's definitely a really good step up. But it takes a really long time too. Not as long as probably the 3-dimensional, but still pretty long time, because you're not cutting strings to get everything the right length and all that stuff. And finally, software. So software is the visual-oriented stuff. We use it in class, and I think, honestly, that is probably the most effective thing now, because everybody learns pretty well visually. Most people do. And if you really have to understand a concept quick, software is definitely the way to go. So there's the 3. So those are the 3 methods for me. So whoever's stuck, they can definitely figure it out that way with those 3 methods for learning things to visualize stuff. All right, now we're going to go to section 2. So we're going to graph something here. So let's say, we're given a formula here to graph a problem, and it's x squared plus y squared is equal to 4. So it's a simple circle formula. When we graph it on a graphing calculator, it gives us a circle, but when you plot it in 3D space, it's not going to look that way, according to the professor. So let's just use some software to plot it real quick. So here it is. I already showed it before. You see it, and you've got all the different sets of planes. You got the x and y plane, you've got the y and z, y and x plane, and you've got, that's pretty much it. You view it from those 3 planes, and you kind of have a general idea of what the shape is. And then when you view it from a 45-degree angle from everything, roughly, you get a pretty good visual of it being 3D. You know it's 3D now that you look at it. So what happened? Why is it doing this? Well, z doesn't have any bounds. So whatever we're graphing, when we graph it in 2D mode, we just have a ring. And as we're kind of bringing it out, z does not equal anything. So because z doesn't equal anything in this formula, it's kind of limitless. It doesn't have anything that's bounding it. So wherever we plot x and y, z will exist. So that's basically what this is kind of implying. Z and y exists when we plot this, and will exist infinitely. I can scroll out as far as I want, and the tube just will keep expanding. It will get longer and longer and longer. So yeah, Z does not have a bound. It will basically just take that little suggestion of a radius of a circle, and it will be like, okay, I'm just going to keep layering them on top of each other because there's no bound to it. So there you go. It creates the concept of the cylinder. So yeah, that's pretty much roughly what I would think about it as a cylinder. So you're just kind of looking, so when you look at it in 2D, you're only looking at slices of it. But in 3D, you're looking at the full object and it's extending along the missing dimension that has no bounds. So it's creating that infinite tube that we have. Now we're going to go to the third question. So our third question is, so when we graph something, we're gonna go ahead and discuss it. It's going to be this graph here. When z equals the radius, what happens? So when z equals the radius, we get a cone. Why do we get a cone? Let's take a look at that. So the cone, and I graph it here from both sides. I get the negative and the positives of z, and I get a cone. So this is kind of like this concept of the cylinder, except what we're doing is we're involving z. But how do we involve z? We make it equal to the radius. So what's the formula for the radius again? Well, we already saw it. X squared plus y squared equals the radius. And the whole thing is going to be graphed in cylindrical because we have the parameters r and z. We don't see theta, but it is graphed in a cylindrical way because it has those two parameters. Those are the main ones that we see. So basically the idea is whatever you plot in r as the radius, it basically becomes the radius at that specific height. So whatever, if it's at a height of 3, the radius is going to be 3. If it's at the height of 4, the radius is going to be 4, etc. So when it's at 0, it becomes nothing. There's no radius. When it becomes 0.5, the radius becomes 0.5. That's exactly what we're seeing when we graph this in 3 dimensions. See, you go to 0, yeah, it kind of glitches out. But you go to 0, and you just, as you go out, you go to 3, it becomes 3. The radius becomes 3 of the circle. And it's just an expanding circle. It's literally all of these little rings of circles stacked on top of each other that are all representing varying radiuses, which are all represented by z. So as z increases or decreases, it kind of creates something, the effect of that. So it's almost like taking an absolute value function and spinning it around too. But I mean, I wouldn't say that, but it kind of reminds me of that. And I wouldn't, that doesn't exactly make my point clear, but the point is, you're creating all the radiuses with z. So z is the dependent variable for all the radiuses. So instead of creating a cylinder, we're having bounds that are pronounced by z. So the cylinder kind of goes inward on itself and becomes a cone because the radius varies only with the letter z. See, as I expand, it just gets bigger and bigger. It's just because of the height of z that changes the radius. So there you go. And we can kind of discuss that a little bit further. Let's go to, so that's kind of like that's what I kind of visualized it as, is really it's just the same thing as the cylindrical thing for the cylindrical object, but you're just literally making the radius equal to the height. So that's why it's creating a cone. So 0, and then you kind of go out of 1, so that whole thing becomes a radius of 1, and then 2, and then the whole thing becomes a radius of 2, and so on. So it's literally just going to keep expanding and expanding and expanding until you have a cylinder. And it's going to be the same way in the opposite direction. Z is going to be negative, sure, but when you square, it's not going to matter. It's still going to expand the points out. So you got the negatives, and you can't really, it's going to probably be imaginary, but it's still going to create the cone in the opposite direction. But the general idea is it creates the cone. So that is how the cone is formed in this example. Now we're going to move on to number 4. So we have a student who was messing around on his graphing calculator, and he saw that, P of sine delta, I cannot remember what this one was, sigma, P of sine sigma, make up something that looked like a donut, whereas when he tried graphing the other, P of sine theta, it looked more like a moon. Both theta and sigma are supposed to be angles, so why don't the shapes match? Well, I'm going to look through my notes here just to kind of prove it. Let's just go back to the concept of the difference between cylindrical and spherical, okay? So when we graph something that's spherical, we put it out on two angles, theta and sigma, and then now I remember the p is rho. Sorry, rho equals to this and rho equals to that. So we graph those two out, and in our one version of the formula, we have that, and it goes to rho. So the angle goes down, and then rho comes out. And when you rotate it around the z-axis, as this varies, it kind of just creates, it only changes over here. So as you rotate it around the axis, it's a very simple rotation because you can just you can easily vary the rho's length, and sigma's angle, and it will kind of just create whatever the shape was that you were trying to create. So because it's rotational in that way, and its angle is based off of the angle with rho between z and y in the plane, it creates the donut. So let's just kind of demonstrate that. It creates the donut. So there it is, not this one. There it is with the sigma symbol. We rotate it in, and it's just it's basing it off of the angle. So the angle is basing itself off of the donut. And so it creates a very consistent shape because it's just coming out of z and y. It's just coming out of the plane between z, y, or z and x. So it's just rotating around really easily, and it can vary in shape and all that stuff, and it will create roughly this strange-looking shape, this donut. Now, when we graph it the other way, and we look at it in the point of cylindrical, because that was spherical, now it's cylindrical. In cylindrical terms, we're going off of theta, and theta is based off of the horizontal plane instead of the vertical plane. So because it's not based on the vertical plane like the other, when we rotate it around, it's going to look different. So it's going to create a lobe kind of look when rotated. And that's exactly what we get. So when we rotate something like that, as you can see, well, I kind of left the bounds a little bit too big because it's supposed to look like partial lobe, but 2 pi. But as you can see, if we just kind of change it out to look like the half moon shape, yeah, that's not going to do it. But it looked like a half moon shape before, but you can still see it. If we rotate it around the z-axis, it doesn't look like that. It looks very inconsistent. This is the z-axis. It looks really strange. It's creating this kind of strange looking kidney, I guess, red blood cell looking type of thing. That's only because I'm on the wrong set of bounds. But it was a half moon originally. So this shape is really dependent on whatever the horizontal angle is. So as it rotates, it's literally just kind of basing off of that circular motion. And then it's kind of going up and down and up and down and up and down and creating all these little rings to create what the shape is supposed to be within the formula. At least that's the way I interpret it. So yeah, you're kind of graphing it, and you're having a completely different, you're basing off of a different plane. So it's, in general, that other plane is going to affect how this equation is going to look, even though it is the exact same equation. And I have an even more basic example. If we graphed this, right? If we graphed this whole thing, let's just say I graph it here, and I change the variables to instead y equals x. And I extend it to 3D, this is what's going to happen. It's going to look like a completely different thing. So it's literally basing itself now, it's just because I'm doing it in the Cartesian method instead of spherical or cylindrical. So now what happens is we're basing our rotation, there is no rotation because it's Cartesian. You're just basing it off of x, y, and z being put down in one place. So there is literally nothing rotating it. So that's why it looks like the shingle for a roof. It's just, there's no rotation, so everything is plotted exactly where it wants to be plotted. There's no mention of angles. And when we do, when we look at z, it's similar to what we did with the cylinder. Z just extends out because there are no bounds on it. But my point is, when we go in each different method of graphing, we will see it change. It will completely plot itself in a completely different way because it's basing the point that it's the individual points that it's plotting off of the different sets of axes. So you will if you try to graph one formula and flip out the variables to basically make them relevant to their specific set of parameters that you're doing, whether that be for Cartesian graphing or for cylindrical or spherical, you're going to get a lot of different things, different shapes. So yeah, that's just kind of the general idea of that. So yeah. So that's kind of what my view is on that. So that is why it's going to look like that. There are supposed to be angles, but they're not going to match because they're angles from different points of view, different sets of planes. So when we did the spherical one, this one was the one that looked like a donut. It was based off of the vertical between z and y or x and z. Whatever was between z, it was off of that vertical set. And then we have it here. It's based off of the horizontal between x and y and not z. So as I said, they're going to look completely different because of that and create different shapes. All right, now we're going to go on and we're going to move to the next question. So 5, we're looking at a really cool shape, space curve called the Lissajous curve in class. So it twists around a bunch and it looks like a web that's all connected. But when we tried plotting it, it looked like nothing was supposed to. Like it was supposed to. It just seems like a parabola. They don't really know exactly what it looks like. So let's help them make it look right. So when we graph this little formula, right? The thing that we see in the picture is we see that the bounds for it from t are 0, less than t is less than 2 pi. When we limit ourselves to 2 pi with this formula, this is what happens. So we have sine t over 2, sine t over 3, and cosine t over 4. Let's just do a really basic thing just to make this really easy. We're going to plug and chug it. So when we put sine of t at 2, it's going to be sine 2 pi over 2. Then the other one, sine of 2 pi over 3, and then cosine of 2 pi over 4. What is the problem with this? Well, the reason why we're going to only see a little segment of the whole thing, of what it's supposed to be plotted as, is because you're going to have basically kind of, it's hard, let me rethink. Basically, each of these formulas, right, sine and cosine, all go off of the concept of oscillation. They repeat themselves after a specific number of counts on the coordinate grid, specifically in the variances of pi. Every time we rotate through 2 pi, sine resets. Every time we rotate through 2 pi, cosine resets. They both have a specific point in which they reset, a very specific pattern. That's what the oscillation is. That's what an oscillation is, a repeating pattern. So the periods of these formulas are very different. The period of sine of t over 2 is going to be 4 pi, right? Because if it's 4 pi over 2, it's going to be 2 pi, which equals an oscillation. And then with this one, for 3, it needs to be at least 6 pi, because 6 pi over 3 equals 2 pi, which equals oscillation. And then for this one, for pi over 4, or t over 4, it has to be 8 pi over 4 to make that oscillation. So when we don't have that, which is what we have in this example where it says on the interval of our teacher showed us, which was 0 to 2 pi, all we get are pieces of it. So 2 pi over 2 is going to equal pi. 2 pi over 3 is going to be 2 pi over 3. And, 2 pi over 4 is going to be basically pi over 2. So as you can see, the value gets smaller. So from each angle, we're only going to see a smaller and smaller and smaller piece of it. And these are relative to each plane. So, x, y, and z. So let's go ahead and look at it now. Let's see. So here it is on the interval, in the exact interval to 2 pi. So as you can see, when I show you the z and the y-axis, or sorry, the x and the y-axis, right? We're only going to see basically the melding of the two portions, or the melding of the two formulas that they make up as the sine and cosine, or the trigonometric equations that they're using. So we're only going to see that little piece and figure that out. So what is the number that we need minimum to figure this out? Well, I think what we need to find is the least common multiple of the numbers. So basically what we see is we need 4 pi when we have, well, basically we need 4 pi over 2 to make 2 pi for this. We need 6 pi over 3 to make 2 pi. We need 8 pi to make 2 pi, right? So we're going to take those 3 numbers and find their least common multiple. So what's the least common multiple of 4, 6, and 8? They all have, they don't have 16 in common, 12, 20. They all have 24 in common. So that is our least common multiple. So in theory, if we have a minimum of 24 pi for our bound, we will have the full view of the formula. Or not the formula, but what the graph is supposed to look like. So let's go right ahead and do that real quick. 24 pi. So if we do 24 pi, we have the exact strange shape that they were talking about, which I looked up this shape, and most of the things that I saw on YouTube were pretty much like this. They were in, what are they called? How do you say it? I'm forgetting basic stuff right now. It was a... what is it? Oscilloscopes. Yes, oscilloscopes will actually show you this axis specifically, like these sets. You can see the y and the x. They'll show you this view. I don't know if they show you z, but they will. That's what I remember seeing is this view. But it looked really cool. And so, yeah, this is exactly what we want to see. You see there's no cuts in anything. Nothing's missing. So, yeah, there you go. That is how you see the whole thing. You have to find basically what the least common multiple is between the 3 to get it. So once we got that least common multiple, we found the minimum number that we needed to put into the bounds to view the whole formula. Now, another thing. Why would we need to... another thing that I thought about was why would it be 0 through 24 pi, and why wouldn't it be like negative 24 pi through 24 pi? Well, the reason is because negation isn't going to change anything. So, if you put a negative sign into it, it's just going to create a reflection. It's not really going to do anything. It's going to trace the same shape in a mirroring way. So it'll extend into that negative direction, but it won't fill out the curve any further. So you're literally just you're just layering it over itself again, and you're not really going to see any difference. So really it doesn't matter in this formula, in this way, when we're doing a trigonometric 3D visual. So, yeah. That's basically what I've learned kind of figuring all this out on my own. And yeah. So there we go. That is how you kind of find the bounds for a formula like that, is you find that least common multiple between the 3 different sine functions, and you get roughly the minimum bounds you need for the shape when you plot it in 3 dimensions using the 3-dimensional stuff in software. All right. So now we were done with those 5 questions. So what's our final thing to do? Well, now we're going to go right ahead and look at the final moment here to reflect. So let's see. I had to kind of brainstorm a couple of different ideas. I think like the most important thing was kind of explaining the math behind it and trying to make it as simple as possible, because I know that this is supposed to be for a beginner student. And when I read through our teacher's parameter stuff, he said you can't really you can't, it sounded like he didn't want us to use a lot of math. So I just tried to make it really simple for the student. So hopefully that's what I've done. And I liked the process in a way because I had to do some fun little creative things. Like I came up with some ideas, like the 3D idea that I came up with for the in-person thing, because I was like complaining about how you couldn't touch it, you couldn't feel it. I am a tactile learner sometimes. I like playing with stuff. I like making Legos. I used to like making Legos as a kid. I still do. And I wanted to come up with a way to make it more tactile. Maybe I can try building it. I don't know. Maybe my teacher can give me extra credit. But I came up with that way in my head because I'm so imaginative, and I just thought it was really cool. So I think it was really fun. I learned something with that, and I hope that probably that explanation of making a little 3D thing especially would help a student kind of taking Calculus 3. It might make it a little harder for them though. It might take up too much of their time. That's why I like the drawing idea too. I was kind of like, what is there? I had to kind of like think about it. I'm like, is there a way to draw stuff in 3D? And I'm like, yeah, we do it all the time. We draw it in this way. But I had to figure out exactly what that concept is, and if there was a way to make it in paper. So I kind of looked through illusions online, and when you look at illusions there, I'm like, what are they called? And the concept was isometric illusions, I think. That's what it was, something to do with isometric. So I found isometric paper, and I was like, oh, is this used in math? And I'm looking, and it seems to be. It seems to be a concept in like calculus and stuff. So I thought that'd be a great idea for a class, is a student using isometric paper to figure out how their stuff is going to be when they're in Calc 3. So yeah, I guess that's going to have to be a new thing that kids are going to have in their books now, is isometric graphing paper. But I've never seen isometric paper in person before, so I'm maybe saying stuff like this will encourage people to start using it. I don't know. Now, how do I feel about my ability to understand these concepts now compared to before I started? Well, understanding stuff like with the really simple math like this for the final question, actually, that was the most influential thing, and just really figuring it out based on the least common multiple of the 3. I think that's definitely going to help me when I'm doing more trigonometric functions, because I really suck at trigonometric functions. So, yeah, I found that tip somewhere, but it was really cool. Just the least common multiple between, if you want to try it, find it between the couple of points, and then that way you can kind of figure out what it's doing. So, and I liked it. It was really cool. So yeah, I think that's definitely going to help me. I've learned a lot from that. And then, yeah, I think those are really my main points. And then also, I still have had a little bit of confusion between cylindrical and spherical. But, after doing this, I think, honestly, I have a better understanding of cylindrical and spherical's differences. So, yeah, I think overall I've done a lot better with this. And, yeah, so I'd say I've done better than